Okay, so it's a great pleasure to have Vincenzo Vitelli from University of Chicago, and he'll talk about non-reciprocal phase transitions. Yeah, you can start.
Well, hi everybody. Good morning, good evening, whatever your time zone is. Good afternoon. It's a great pleasure to be here to discuss this rather recent work done in collaboration with two brilliant postdocs, Michel Fouchard, who is here still in Chicago, Ryo Anai, who is in Korea, and with my collaborator and colleague here at the University of Chicago, Peter Littlewood. It's a work that spans various areas and has application from classical to quantum physics. I'll try to give a sense of that, perhaps biasing a little bit more towards its classical aspects. One thing that I would like to say from the very beginning is that in the simple case that we're just seeing, in the study of an Ising model, this phase transition can be described in terms of a change in the shape of an energy functional. For example, going from a single well to a double well. I'm not going to delve into the details, of course, because they're familiar to everybody. I would like to also point out that in many cases, even when we consider quintessential example of non-equilibrium phase transition, like the flocking transition, and it's very appropriate that Hugh reviewed extensively all this literature. Even the flocking transition, which consists essentially in a number of flying spins displaying spontaneous alignment. Let me just recap what Hugh just described as a Vixek model. Imagine having a bunch of spins moving in a plane. The spins can move, so you could call them birds if you prefer. And a simple discrete rule that you can use is that you look in a neighborhood, let's say this bird here, and you take an average of all the direction, and then the new bird, this bird at the next time step will move in that direction given by the average of its neighbors, plus some noise. Okay? And so this simple rule, when you iterate it, gives rise to an interesting phenomenon. When the noise is low, when the density is sufficiently high that the interaction favor alignment, you will find a so-called flocking phase, in which, if you can see this movie, especially the one on the red, you see all these birds moving in a fixed direction in space. If you like, the velocity field as an average, which is well-defined and clearly non-zero. But if the noise is high, there will be a disordered phase in which all the birds fly in random direction, and the average velocity is close to zero. Okay. Now, this transition is clearly an out-equilibrium one, as Hugh explained in much more detail and level of sophistication with this. At least the canonical analysis still utilizes notion of minimizing an energy, of deriving the dynamics from an energy function. Okay, so the thing that I like to study today are cases in which you have phase transition, but you can't start from an optimization principle. Or in other words, the dynamics does not follow from an energy function. Okay, and I'm going to focus on a specific case, perhaps, where this occurs rather naturally. I hope to convince you. And so, in a sense, in this world, phase transitions are inherently something that you can describe using hydrodynamic theories, but less using and optimization or energy minimization considerations. And so many of the systems, in my opinion, the most appropriate way to view them is to spatially extended dynamical systems. Okay, so let me try to be a little bit more specific. In what sense or under what condition mathematically I will not be able to generically define an energy function? And let me enter, at least in an abstract way initially, and then I'll give a bunch of examples, the notion of non-reciprocity, or at least the way I would like to use this word today. So imagine that the system that you want to describe is composed of many fields. Let's say at least 2 such fields. These fields could be I don't know if you were describing a system composed of two species of birds. Could be birds type A and bird types B. If you were you could also use it to denote just different Cartesian component of a vector field, or a tensor field, as I'm going to show you momentarily. But the crucial thing is that if you even just consider an energy functional, which is a quadratic form, please steer behind this awful black line. This quadratic form, of course, will couple the two types of field, VA and VB, via a matrix, which is this matrix A. Okay. Now, if we say, and of course, I mean, typically the dynamics of these fields will be derived from a variation of this energy. This is an example of a conservative dynamics. Okay. Now, what I would like to draw your attention to is, let's look at this matrix that tells how these fields couple to each other. Now, I would like to call today non-reciprocity, and I think it's a fairly common usage of that term, the following fact. I want to consider explicitly that field A will interact with field B in a different way the field B interacts with field A. Okay? So in other words, the matrix that couples the fields, the matrix of coefficient cal A, I want it to be non-symmetric. What does that mean? It means that you can split it in an even part that is characterized by the fact that this matrix is unchanged when you flip the indices A and B. But if it's non-symmetric, there will also be an odd part. And you will hear in this talk a lot of this word odd showing up in various contexts. What we mean is that when you flip the index A and B, or the relevant group of indices that you can imagine in a tensor field calling by A and B, then the sign of the entries of this matrix is flipped. Loosely speaking, that means that the way the field VA interacts with VB is the opposite way in which VB interacts with VA. Now, it doesn't have to be opposite. It's enough that it's different, because if it's different, it can always be split in a part which is even and in a part which is odd. And of course, the simplest example of an odd thing is just this matrix here, this perfectly antisymmetric matrix, which is manifestly satisfying the property we're saying. Now, imagine, however, to take this odd part and stick it in this energy, in this putative energy function, where this AAB, which is this perfect antisymmetric matrix, will multiply this combination, which is symmetric, which means that the energy will be zero. Or in other words, any dynamics that pertains to fields that are antisymmetrically coupled cannot be derived from a minimization of an energy, because that energy will not exist or will be vanishingly equal to zero. Okay? I'm going to give an example momentarily of how this can happen in a simple situation. But this is the general frame that we want to understand. So phase transition in system composed of at least two fields that interact with each other in non-symmetric ways, such that the dynamics of the system is non-conservative in the sense that its dynamics cannot be derived from minimizing a potential energy. Okay. If there are questions at this stage, I would be more than happy to take them. And of course, please notice that here I didn't write all the quartic terms, all the derivative terms. This is just an example of why non-reciprocity defined in this way will naturally imply this difficulty or this impossibility of, like why non-reciprocity implying non-potentiality, if you like. Questions?
Can you kindly comment a little bit on the nature of A and B, these indices? Can this be extensive indices like, the number of particles, or it is something related to the symmetry of the system? Or
so I'm going to give a few examples momentarily. At this moment, A and B label the type of field. So let's say that there is, I don't know, particle blue and particle red. Then each A and B can run from 1 to 2, and this index label the type of particles. However, if you had a vector field, it could be also the X and Y component. In principle, anything that I'm saying is valid for all of these cases. It could be also a tensor, and I'm going to give you some example momentarily. I just wanted to define in purely mathematical terms at first. Okay. Now,
Vincenzo, a small comment, which
please.
is that one more kind of non-reciprocity you can have is a kind of provisional, that it's not that there's two permanently labeled species A and B. You can have a non-reciprocity when you've got one creature at the back and one creature in the front.
Absolutely.
And even though they're the same kind of creature, their frontness and backness allows you...
Absolutely. This is a wonderful example.
And in fact, you commented that the flocking model, in some essential sense, has to do with minimization augmented by this funny advection. That funny advection can emerge purely from a fore-aft asymmetry, as we showed. So it's sort of, that's the comment one.
I think that I may even have a picture that will illustrate for people who are maybe not familiar what Chiral is saying with an example. In fact, from his work, I think. But the one thing I also want to say is that this non-reciprocity can exist at the microscopic level in the interaction between particles. In this talk, we'll be particularly interested in cases in which the non-reciprocity persists also at large scale in the field theoretic description of these systems, which is not always the case, I must say. Okay, so let me just give you some simple example, right? Well, first of all, I would like to convince you that this sounds strange, but it's actually quite common, even trivial, if you look at dynamical systems that have nothing to do with physics, as people extensively study. For example, I mean, if you were really interested in a bunch of birds, or two species, the falcon and a dove, well, let's say that I should have probably portrayed them differently. But the falcon could interact with the dove in a different way that the dove interacts with the falcon. Most model of ecology built in non-reciprocity in a rather trivial sense. I also should say that, for example, in neuroscience, in this context I'm particularly interested, people study inhibitory and excitatory neurons. They divided into this category, and as the name indicates, they have very different effect on each other. And these are essentially problems of synchronization, very similar to the ones we're going to describe today. And more generally, you could have, like, for example, quite literally metronomes of different types that are programmed in a way that one wants to synchronize, A wants to synchronize with B, but B wants to anti-synchronize with A, okay? Now, if you start moving in the realm of physics, maybe non-reciprocity sounds a little bit less obvious, especially if you think in terms of elementary mechanics, like Newton's third law is predicated on the notion of reciprocity. But that's generally no longer true if you're coupling to a substrate, or if your particle interact with a fluid, or if there are complicated particles. So what do we mean by complicated particle? This is one of the domain of, for example, Chiral study. I just quoted here a paper that you can consult with a bunch of references also to other work. But for example, here is the chemical reality is a bit more complex. These particles have chemical reaction going on. But let's assume let's look at these two particles. Let's try to put the context of Chiral, or comments of Chiral in context. Let's imagine that these were two birds, but this bird that is in front doesn't see the one in the back, but the one in the back sees the one in front. Well, even if they want to align with each other, they have to see each other. So these two particles will effectively interact in a non-reciprocal way. Now, these are not birds, but still you can engineer their interactions if they are mediated by complex chemical processes in such a way that will sort of dance around each other rather than undergoing that simple aligning dynamics. And these things are fairly real. And I apologize if I didn't put here a bunch also of experimental references, but there are studies where this is done. A second example that I want to bring to your attention, again, let me introduce it to a bunch of experiments. It's an experimental system where it's been very recently realized, or signature that have been sent. It's something called odd elasticity. And I'm going to say in a couple of slides what this is for two reasons. One is because I'm a bit obsessed about it. So you should take the emphasis in this talk on odd elasticity with a pinch of salt. But also because, at least to my eyes, elasticity is the domain where you immediately imagine you should think in terms of energy minimization, right? And elastic energy is how I start, that's how I learned elasticity at least. Now, before I zoom in this and I show you a bunch of examples of metamaterials, these are artificial structures composed of sensor and actuators, as well as some recent experiment on spinning embryos that interact with transverse interaction. And these spinning embryos have this transverse interaction because they're in a fluid, so it's sort of like a frictional interaction. And this is common also to colloid, again, spinning in water. But these examples that are on this slide are just, if you like, the tip of an iceberg. And I couldn't even begin to enumerate all the things that fit in here. But I just wrote them in the bottom of these slides. They go from social system to quantum open system, couple lasers. So if you see only 3 slides next on one of them, it's just a personal choice, maybe a bit self-referential too. So let me tell you a little bit about this odd elasticity, so you can see maybe in a specific example, what is this non-reciprocity and how a peculiar description of elasticity can arise. So here it is. So first of all, what is elasticity? How did I learn about elasticity? Well, elasticity, usually thought by sophisticated people to be a boring subject because people learn it maybe early on in their career, although in its generalized form, I would argue, underlines a lot of condensed matter theory, classical and quantum. But the simplest form is this. You start with an energy density. That's how you would learn it in Landau Lifshitz, for example. You start with an energy density, and this energy density is expressed in terms of fields that are they're not just vector field, they're tensor field. There's Uij, which is a strain, gradient of displacement. So gradient in the j direction or displacement in the I direction. And then if you're doing linear elasticity, which is certainly not the only thing you can do, you will build a quadratic form out of it. Again, notice here there's more indices than before. Before there was just an A and a B. Here there are 2 indices. And the coupling matrix is not a matrix, it's a tensor. It's a rank 4 tensor. And this tensor, Kijmn, contains all the possible elastic moduli. So in a sense, this first equation is just the equation of F equal 1/2 kx squared on steroid. Okay, it's the continuum version of the energy of an harmonic oscillator. Now, if the forces, which in continuum mechanics are called stresses, are related to the energy by a gradient of the potential, which means that the forces must be conservative. A huge assumption that we're going to break in this talk, and certainly when discussing odd elasticity. If that happens, if they are conservative, then this tensor here, you can demonstrate, must be symmetric. Okay, so let me restate it because I got a bit discombobulated in my chain of thought. If the stress can be derived as a gradient of an energy, so the system is potential, then there is a symmetry that this tensor must satisfy, which is pair index I and J and pair index Mn can be flipped with each other, and this tensor is symmetric. Okay? This is just a version with 4 indices rather than 2 of what I was showing you in the previous slide. And now, what we are interested, the reason, and then of course you can enumerate then, putting additional symmetry like isotropy, rotational invariance, all the possible moduli that you can have. Bulk modulus and shear modulus naturally arise as the only 2 possibility when the system is isotropic in 2 dimensions. Okay, and of course that will tell you how a structure will deform, a passive structure. But now look at this thing on the left, which is from Corentin-Coulet recent realization. I'll tell you more later. Now this structure here, like many things in active matter, all things in active matter, they're defined like that, as you remember from Hugh talk. They're not just passive structures, they're motors in there. Now, this thing here has motors in it. So when it responds to deformation, it can respond in strange ways. And you can ask, okay, can we classify all the strange ways in which it responds by simply removing this assumption that the forces are potential? Okay. And initially, we can do it in a way that is completely blind to microscopics. Or at least that's how we proceeded, maybe because of, but now we have several examples that have been realized, both artificially and in nature as putative description. So let me show you what happens. Well, the only thing you have to do is you have to remove this assumption. In other words, you say that the forces are no longer gradient of an energy. If that is the case, work is no longer a function of final and initial state only. That means that we are allowing for configuration-dependent non-conservative interactions. So they still depend on displacement, not velocities, for example, but they are non-conservative. That means that the curl of the microscopic forces is different from 0. As long as this condition exists, this is a generic description. Okay? And then it's pretty simple to generalize because you say, look, this relationship between stress and strain is just a linear relation. It's the equivalent at the continuum level of F equal Kx, right? Now, this linear relation can exist irrespective of an energy. Okay, so if you want to find everything that is possible, the only thing you have to say is, look, this coefficient on top of the even part, that is to say the matrix that is unchanged when you flip the index I and j with an n, has to have an odd part as well. And if you augment the stress with this odd part, and by odd I mean a tensor whose entry is flip sign when you switch I and j with an n, then you can enumerate everything that is possible beyond ordinary elasticity when you assume for non-conservative interactions. Okay? Are there questions on this point? No? Especially for people who see this for the first time, I would be very delighted to delve with with clarification if you want. So if there are students, especially in the audience.
So the material you showed there, and what exactly do you see? I mean, like which shows that you have this odd part.
Well, so here you can sort of see that what I'm saying. The logic here that I'm saying is that let me see if I understand your question. Like what I'm saying is that if I assume conservative forces, this matrix KIJMN has a symmetry. But if I want to find a generic description of linear elasticity, which is defined by a linear relation between stress and strain, that does not assume conservative forces at the microscopic level, the only thing I have to do is to augment this matrix is to remove that symmetry that I had artificially imposed. You see, like what I'm saying is, if you read Landau-Lifshitz, you will learn this, okay? But this follows from assuming that forces are conservative. And now, if you want to do a theory with non-conservative forces, the only thing you have to do is to remove this assumption. And the way you remove it is by allowing this tensor to have both an even and an odd part.
Right, yeah, no, so my question was, you had this figure on the left with ABCD. I mean, so what exactly do you see which tells you that you have this odd part?
Yeah. What you would, the characteristic that defines it, sorry, just a second. So first of all, I'll do it in a moment. So in short, the telltale sign is that you can take your system, do a cyclic quasi-static deformation. So you start it, you deform one way, you deform another way, you return to the starting point. If the system was conservative, the work would be zero. Whereas for a system that has this feature, there can be work generated during a cycle of quasi-static deformation, generated or absorbed. So in a sense, the feature of this medium, the telltale sign, is that if they undergo a cyclic deformation, energy can be extracted or pumped in. What you can also do is you can say, well, besides that, they will deform in strange ways, right? And so if you do a representation of this tensor in terms of, if you write this tensor as a vector by decomposing into a basis of polymatrices, you can find that besides the bulk and shear modulus, that are the ordinary one, the couples, say the bulk modulus couples isotropic expansion to pressure, the shear, the mu, there is the shear modulus couples two types of different shears. There will be two new moduli, which we denote as K naught and A. Please notice that in this thing, you assume also that you don't couple to a substrate so that all these entries are zero because you want a global rotation not to have, if you assume that a global rotation will not generate stresses because it keeps the distances between the particle unchanged, then everything would be zero on this axis, and there will be only two new moduli. I think there's Ananyo raised their hand. Maybe Ananyo, go ahead if you have a question or comment.
Hi, Vincenzo. So hi. The point is, if for you to have A even, I guess you need a substrate because A cannot be angular momentum conserving, right? Because the stress is no longer symmetric if you have A.
Yeah, absolutely. The stress is no longer symmetric. But what you could have, I think we have a couple of examples in our paper, is some internal mechanisms that by generating angular momentum internally can still give you an A. Generically, most of the application I know that display an A, there's things which have a torque density and they're on a substrate, and then you will also have an additional coefficient here. But even if you put an additional coefficient, the part that I want to stress is that what's really important is not so much whether this is A and this is 0. What is important is that whatever is on this side and on this side is different. They're different from each other. Same thing for this one here. If you had an anisotropic system, you could also couple the shear, but you would couple them in a symmetric manner. Thanks for the clarification. Let me also say one thing more here. So what is this A coefficient? What this A coefficient in this simplified form says, I compress my medium, say I make a little square a little bit larger, and as a result of this coefficient, I will experience some torques. Okay. Now this will happen generically in any medium made of spinning unit with frictional interactions. Why? Because in those systems there will always be a torque density, right? Torque density doesn't mean just the torque on each particle that makes a spin. It really means the global torque that it comes from things that want to spin with frictional interaction. Now, if that ambient torque is density dependent, an A coefficient will always emerge. And that's why people sometimes say that, loosely speaking, this odd elasticity, it's a coupling between compression and torque. But that is not how I like to think about it. In fact, if it was only that, it would be kind of trivial in my eyes. And you can see that by noticing that if the A coefficient is 0, you can still have odd elasticity only in this lower part, the K0. And that is in the symmetric part of the stress tensor. So, and in fact, the experimental realization done in the Cooley lab precisely pertain to that system. But before we get to that, let me tell you one thing. So what is this cycle that Abhishek was asking? What's the signature? Imagine that I took those hinges that you saw that Corentin made with robots and sensors, and now I deform them, like he was doing with his hand. Or this system can even do it spontaneous, like nonlinear work cycles. If you read the paper, you can learn about that. But they say that you do this, or the system does by itself, this cycle. Now, the system will return to its initial configuration. But since it's a non-potential system, it can generate energy. And this energy can be used, for example, to propel the structures, to control impact absorption, or even to support waves in a distributed system that are completely overdamped. This is a representation of that. This is a diagram with the two modes of deformation. If you go along a cycle, work gets generated in a way that is proportional to the area times K0, which is the moduli in question. And the way Corentin realized it is it has essentially an interesting system that we proposed, I think, in this Nature Physics with active hinges. In this system, there is only bond bending forces that are programmed. So the A coefficient is equal to 0. There's absolutely no torque density, no coupling between compression and torque, but there is still the K0. Okay. Now, I would like to say that this would generically, this K0 is the elastic equivalent. That's how we had the idea in the first place, of something that was invented a long time ago. It's a phenomenon called odd viscosity. It's common in the study of plasma, where it's called usually gyroviscosity, measured both in Leiden in the 60s in molecules with dipoles and interacting with non-central forces, more recently in colloidal fluid by William Irwin, and here at UC Chicago, and in 2D. And the characteristic feature of this fluid is that they're particles that when they interact, they move transverse. Okay, and that is another microscopic model that would generically, due to this frictional lubrication forces, give rise to odd viscosity in the fluid and odd elasticity in the solid. I'm mentioning this connection because there is this recent paper that, at least in an edited version that will appear soon, is called Fluctuating Hydrodynamics of Chiral Active Fluids. And it will be updated on the archive. The version of the archive is a slightly different title. But the point here is that this connects also to systems like electron fluids. And people before earlier in this talk, in this series, talked about that. Okay, but I'm not going to go into that. So that's to say, in the same way as there is odd elasticity, there is also an odd viscosity if you study fluids with similar properties. But especially for the specialist in the audience, I would like to deliver the point that, to my eye at least, the most interesting thing about elasticity is when it emerges in the absence of an ambient torque. So it's not just a perturbation of a torque that already exists. It could be also this unusual coefficient. And to do that, at least the implementation I know are in robotic matter. So systems that have sensors and actuators. So they don't have to just respond in a way that nature demands, but they have an expanded sense of response. Now, believe it or not, maybe I should go a bit faster because this was just an introduction. What I want to talk today is not just the mechanics of the system, although I would like to tell you that this is quite interesting. And you can see this as an example of this non-reciprocity emerging. Notice here the non-reciprocity is that the way compression couples to, compression and rotation are treated very differently by this matrix. Notice that these two energies are different from each other. That's the asymmetry I keep referring to at the continuum level. Now, what I would like to talk today, though, is phase transitions. Okay, so let me abandon the complicated domain of elasticity, and let me do a form of an XY model, which is non-reciprocal interaction. So how would it look like? Let me simplify a little bit. So the normal easing model, the normal XY model, if you can imagine as a grid with a bunch of spins, planar spins, so they can be oriented anywhere in the plane. And usually you assume that, say, the spin I interact with the spin J in a way that are symmetric. So Jij is equal to Jji. Okay, now here I and J represent the spins that exist in this discrete model, like here, here, or here. And now when this matrix is replaced by just a number, which is the exchange interaction that is usually done and is greater than 0, then you write down this Hamiltonian for the XY model. And you can write down dynamics inherited by the variation of the energy functional in the following way. And that's what usually is done. And usually, but there are people who have considered also the case in which this matrix is non-symmetric, most notably Chiral among others, and us too, more recently. So what does that mean? Well, imagine that your spins are not spins, but they're some little structures or robots or even natural system of the type that I described before that have the following property. Let's say in this case of these robots, they can be oriented anywhere in the plane, but say robot in red wants to align with the robot in blue. A robot in red wants to align with the robot in blue, but robot in blue does not wants to anti-align with the robot in red. That's to say, JAB is different from its opposite is minus JBA. Okay, since these are robots, you can just program their interaction. It's not a particularly sophisticated exercise. It's just a little demonstration, fun, especially for our age. But you can ask, well, if you program this system to have this interaction at the microscopic level, first of all, how would the dynamics look like? What happens? And before we look at the answer to that question, notice that if the red and the blue are interacting in perfectly opposite way as non-reciprocal spin, then Jij equal to minus Jji. And as a result, we can no longer construct this energy function. However, we can still write down the dynamics. It's just this Jij is no longer restricted to have the asymmetry of being symmetric under I and J inversion. You see, Abhishek, this is another example of that matrix appearing again. Now the question is, well, for the XY model, we know what happens. So what happens for this model? Well, if you just do this little toy and you let them play as a movie, you can sort of get a picture of what's going on. You don't need this movie. You can do just a simple mathematical analysis. In fact, we will do more sophisticated thing momentarily. But what happens is the following. Notice in this movie, we have not put any external torque. So if I put down one of these robots, it will not rotate. However, due to the frustration interaction that A wants to align with B, but B wants to anti-align with A, they will, if you like, go in this perpetual motion in which they will chase each other's directions. Okay, and now let me stress that the direction of rotation, the sense of rotation, is spontaneously broken. So chiral symmetry is spontaneously broken. It could have gone clockwise or counterclockwise with equal likelihood. Okay. And the other thing that I want to draw your attention to, and that's why I like these movies, because they're very visual, very vivid, great tool to express it in a simple way that maybe the equations do a little bit less well, is that the result is not a static configuration, but it's a dynamic phase. And this is the emergence of these phases is what we want to study today. And in particular, how do you describe them as a field theoretical element? Okay. Let me try to trivialize what you see, and let me tell you why this trivialization is not enough. Imagine that you had these two robots, robot B and robot A. And now let's try to imagine a step-by-step movie of what will happen. Let's say that robot A, and sorry, first of all, I'm gonna, from now on, represent robot A like a blue arrow, and robot B as a red arrow. So robot A wants to align with robot B, but robot B wants to anti-align with robot A. Why is that? Why is this non-reciprocal microscopic interaction sufficient to explain, at least to zero order, some feature of that circulating or chasing motion that you see? For the following reason. So if they're in this initial position, now robot A tries to align with robot B, and it will move a step, it will try to align. But this robot will want to anti-align with it, so it will do this. But this will want to align, so we'll chase it. And this will go on forever. And that is essentially part of the story of what you're seeing in that movie. Now, the reason why I was saying that you don't need the robots to figure this out is that you can just write the equation for 2 degrees of freedom, the angle theta A and theta B, since if you only consider the 2-particle system, the 2-robot system or 2 non-reciprocal spin system, and then the JIB will be equal to 1, and the JBA will be equal to -1. And so the equation of motion for this for just 2 systems will be the ones that you see here. Okay. So now in this equation of motion, if you will indeed find that when JB is equal to -JBA, there is this chasing motion that I just described. But the thing that I find particularly interesting and maybe less trivial is that actually this two-particle analysis immediately reveal an instability, or if you like, the fact that if I add a small perturbation and I don't make it perfectly non-reciprocal, so it's not perfect, it's not that JIB is exactly -JBA, but I put epsilon in it. A minimum amount of reciprocity, even microscopic, namely if I put that besides wanting to chase each other, they also want to align a little bit, it will immediately destroy this motion that I described, that I showed you. So any small amount of reciprocity will kill this phase if you had only 2 agents. So the question that we set out to answer was, if we put many such agents, and we did a bunch of things like kinetic theory, to go to the hydrodynamic description, field theory, you'll see a bit of it. If you have many such agents and noise, can this motion that is unstable at the level of only 2 particles be stabilized by many body effect and noise simultaneously? Now, at first, you may think that that may be complicated, that actually having many particles could possibly even be worse. In a sense, you already know that if this is spontaneous, as I'm claiming, is a spontaneous symmetry breaking between clockwise and counterclockwise, is a bit like an Ising model. So you could imagine you could flip between clockwise and counterclockwise periodically with an escape time that is the lifetime of the chiral phase. However, the crucial point here is the following. If you make the system, and this indeed happens, and in fact, people who had tried to look for these things in optics before had seen systems of 2 resonators or 2 ring resonators like Christodylis et al. Flipping from one state to the other, from one chirality to another, like first like this and then like that. However, notice what happens, and simulations corroborate this simple analysis. If you write down as you can, a simple dynamical equation for this process, there would be a noise in it. Now, this noise has a variance, and this variance by the central limit theorem, and in a way that you can corroborate with simulation, goes like 1 over square root of n. That means that if you put into the Cramer's formula, the n will go in the numerator. So this chiral phase will be stabilized whenever the number of particles goes to infinity. When that happens, then, at least in a uniform system, in some portion of the phase diagram, you could actually have a stable chiral phase. At least this argument suggests that. Now, if you run a movie, you could do the following. Instead of, you can run a so-called non-reciprocal XY model. What that means is that you do the same thing that you described and the thing that I also described at the beginning. But now you have two different particles. And they're self-propelled, but the particle in red wants to align with the particle in blue. But the particles in blue want to anti-align. And now what I want to show you is what happens when you just run a simulation in the right range of parameters. In some range, they will just do random things, it will be disordered. In some range of parameters, they will both move in an aligned way. But another possibility that occurs is this motion that I show here. So in other words, what you're seeing here is this chasing motion that would have happened with two robots, but it's stabilized. Even when you put a little bit of reciprocal interaction, actually there is this, you find that the velocity field of the A and the B make a fixed angle with respect to each other, but they rotate constantly. And the more particle you throw in the simulation, the more stable this motion becomes. You could call it a chiral phase. It's not phase in a thermodynamic sense, but this is the phenomenon that we're trying to describe. And if you wanted to model it, the way you model is you write down the same equation for the XY model. So there's an angle, and then there is a motion of the particle in a direction dictated by that angle. There's a noise. The only thing we've changed is that since we have two species of particle, the coupling between them can be asymmetric. Okay? This is by no means the only example of a non-reciprocal thing. In fact, our paper has several more, but it's certainly one that is quite vivid and show what's going on. There's one thing that I want to draw your attention to. Unlike the normal easing model, unlike the normal flocking model, where the velocity field was fixed in space, the birds were moving, but the velocity field was fixed in direction. These phases are characterized by rotating order parameters. Okay, so not only the individual particles are moving, the whole order parameter, it's a time-dependent phase. Okay, if there are people who study time crystals and things like that, may find interesting analogy with phenomena like that. So how to understand the origin of this time-dependent phase? Since we don't have an energy functional to minimize, we're only left with an hydrodynamic theory to analyze. Now, first of all, let me... Vincenzo,
a small question.
Yeah.
You know, if you take the model on, just go back to that slide. Yeah, if you take, So if you split the Jij into symmetric and antisymmetric part, it is as though there's a Poisson bracket between theta I and theta j proportional to the antisymmetric part of Jij, and a dissipative Onsager coupling proportional to the symmetric part.
Well, actually, I don't know if you...
Does that work? I'm just curious.
I don't. I would have to do a bit the exercise offline, but
okay. So
usually the Poisson bracket techniques. Usually the Poisson bracket techniques works for systems that are Hamiltonian. For example, odd viscosity can be described with Poisson brackets because I can essentially write down an Hamiltonian. Here you would have to be careful about that part. Meaning this system is clearly non-Hamiltonian.
No, absolutely. What I mean is the following: that it's the antisymmetric part of the coupling is kind of Jij is kind of mimicking a symplectic dynamics between theta I and theta j.
Absolutely.
And the symmetric part is a dissipative dynamics between theta I and theta j. So I'm just wondering if in some limit this problem doesn't become like something with an energy function which is still the old cosine theta minus theta j, and one piece is a reversible coupling and one piece is irreversible. But I guess you're right, one will have to do the algebra.
One has to do the algebra. One thing I can tell you is that we tried for one case, not this one, but something more close to the odd elasticity, and we could write down a complex Hamiltonian, meaning maybe I shouldn't call it Hamiltonian for the purists, but we could generating function. I don't know how you want to call it. And once we could add, loosely speaking, something like p squared plus ix squared.
I see.
You start doing things like that, then you can actually do Poisson brackets, etc. And you could describe a knot spring in that language.
I see, but that sort of takes it off into PT symmetric land or something.
Absolutely. In fact, we'll go there momentarily.
Okay. All right. I'll talk later.
Yeah. Okay. Now, one thing I would like to stress here is, besides birds and the synchronization, etc., clearly this is a more general problem. And in fact, towards the end, I'm gonna also review a little bit things that other people have done as well, including some of the people present here. But let me just say, what has emerged from this discussion is the need of developing a starting point that is not an energy function. So how do you do that? Well, you say, look, instead of doing the usual thing that we do of starting with an energy and classifying and putting all possible terms allowed by symmetry, work directly with an hydrodynamic theory. This is routinely done in the so-called equivariant theory of dynamical system. So, for example, for the model that we studied here, which is sometimes called Model A or critical dynamics, you start with this equation and you enumerate all the possibilities, you see, including the nonlinear term, including gradient terms that I didn't write on this slide. And what you do is you simply allow this matrix of coupling to display non-reciprocity, or if you like, asymmetry. And then, of course, you will no longer be able to write down the dynamics as a gradient of a potential, but you can still write down generically all these hydrodynamic models with non-reciprocity built in. And then you do the analysis directly on these models. Let me give you an example. In the case that we studied more extensively is when we impose, to write down the hydrodynamic models, a rotational symmetry. So rotational invariance. This O2, for example, in 2 dimensions. Then you can prove that this is the most general answer plus gradient terms. We also derived it from microscopic model, okay? But you can write down based on symmetry consideration. And however, if there is no reciprocity, this A and B would be different from BA, that's the antisymmetry. And this simple description by itself will describe many things, depends on how you interpret it. For example, it can describe flocking if this velocity field, if this velocity field, if this V field is the velocity of the subpropelled particle, okay? But it can also describe synchronization if V is the average phase of coupled oscillators. Or it could describe pattern formation if V denotes the amplitude and position of periodic patterns. And of course, in each of these systems, there is a different, apparently, physically different system, isotropy, time translational invariance, space translational invariance. But in all of these things, they can be folded onto this model because in synchronization, there's a time periodicity. In pattern formation, there's a spatial periodicity that makes the order parameter, the V order parameter compact. Okay, so when considering this equation, we are automatically considering at least these 3 classes of problems. Okay, so if you consider a system like this, how do you understand the transition? Well, let's simplify here and say, let's go back to that flocking model. Let's assume that the J coupling have both a symmetric and antisymmetric part, and we now construct these two components: the sum of JB plus JBA, plus the difference between JB and JBA. If the system was reciprocal, so perfectly symmetrical, what would happen is JB would be equal to JBA. So you would be living on this axis here. So you could have, and then if JB is equal to JBA, you can just call it J, and it could be positive or negative. If it's positive, the 2 species of birds will align. If it's negative, they will be anti-aligned, like an antiferromagnet. And you would have a direct transition between an aligned and an anti-aligned state, a flocking or an anti-flocking state. But notice if I put a little bit of non-reciprocity right here, then I could live on this, along this line. And if I could then go from an anti-aligned to an aligned phase via the chiral phase that I showed you before. And now you could ask, well, what happens along these lines that I drew here schematically, but we also calculated analytically, where you cross from anti-alignment to this chiral phase. To be more visual, let's imagine that the two vector order parameters, VA and VB, are represented here. So VA and VB, when it's anti-aligned, they are static and opposite of each other. When it's aligned, they are parallel to each other. Now, please notice that the order parameters are static. The particles themselves will be moving, like in the started flocking. But when you cross this line and you go in the chiral phase, you start seeing the two order parameters rotating with a fixed angle with respect to each other. And the angle that you have depends on where on this axis you're sitting. Okay, it interpolates from opposite from pi to 0. And notice that here on the x-axis, there is exactly the same thing that I plotted here. So in the chiral phase, you start rotating, and depending on where you sit, you have a slightly different angle between the disorder parameter, but they're always rotating. Okay, and so the question is, how do you describe this transition from this to this that happens, for example, at this point here or along this line in phase diagram? Clearly, we cannot use an energy minimization because of the reason that I said before. This is the non-reciprocity inherently has a non-potential character. But what we can do is to use a mixture idea from dynamical system theory and the non-Hermitian quantum mechanics. So if you prefer the theory on non-normal operator in dynamical system and hydrodynamics. Let me try to walk you through briefly without being too technical. So this dynamical system can be written generically as a set of coupled equation of these forms, okay? And you can define a Jacobian in the usual way, starting from this function f of a. Now, this Jacobian, generically, when you have a non-reciprocal system, will be non-symmetric under exchange of a and b. And in particular, what will happen is that at the point where the transition between the aligned phase and the chiral phase occurs, this Jacobian will develop an exceptional point. Exceptional point is a simple concept of linear algebra. What it means is that you have a matrix, and then at some point that matrix is no longer diagonalizable because the two eigenvectors that are generically, in this case, not normal, will actually coalesce on top of each other. Okay? When this happens, in the collective description of a many-body system, as I'm doing here, and not simply in a two-body system or in a system describing waves, then you will have this type of transition that we are concerned with today. So this exceptional point, it's also quite well studied in systems that are quantum but driven. And I don't have a lot of time to describe this in more detail, but let me just tell you that the peculiarity of this system is that the two modes that are coalescing, of course, they don't describe just the simple structure of the mechanics of each particle, they describe the whole system. One is a Goldstone mode, that represented here in green. This Goldstone mode comes from the rotational invariance, is inherently as a zero growth rate because it's a Goldstone mode. And then there is a damped mode. And when you change this parameter J plus and you hit this critical point, the damped mode coalesces with the Goldstone mode. And what happens is that both of these modes will have a zero growth rate and they will coalesce. And that is the mechanism underlying the phase transition that we're describing, a coalescence of modes in the description of this many-body system, or more precisely, the Jacobian of this many-body system. Now, I would like to emphasize that this chiral phase is by no means the only phase that you can find in this system. If you draw a phase diagram, as we did, calculated, evaluated numerically, and analytically in some cases, what you can find is that besides the chiral phase, that is the one that you show here, depending on the combination of parameters, you could also have the swap phase. So here in this swap phase, a discrete Z2 symmetry is being spontaneously broken. I don't know, in simple terms, what you're going to see is that the red and the blue flip side. I don't know if you can see it. There may be a slight delay in the movie. Okay, so they literally swap their orientation. But notice that it's a discrete symmetry, unlike this one here, where there's a restoration of a continuous symmetry. What's interesting about the chiral phase is that when you started, there was a continuous symmetry because there's this rotational invariance. Then this chiral phase spontaneously restores it. Here, what you're restoring, it's a discrete symmetry. You can also have a chiral swap phase, which is distinct from from the other two, in which you have superimposed essentially the order parameters rotating with them flipping their positions. Now, of course, here there is a bit of a zoo of these things, and I would like to stress, maybe I'll do it a bit towards the end, that there's equivalent of the swap and chiral swap phases also in problem of synchronizations, which have, of course, other names. Now, another thing I want to stress, and I have to say, this is, for me, it's the part that I find most interesting about this work, although it's perhaps the most technical, is the following. Right near the, if you do a simple analysis of this problem, you could draw boundary lines like this one that separate, say, the time-independent from the time-dependent chiral phases. Let's call them exceptional lines because they are lines formed by exceptional points. That's to say, points where the Jacobian becomes, has a coalescence of modes. But one thing that we can prove, and it takes a bit of effort, but it was quite interesting, is that if your system has a background flow, like typically system of self-propelled particles, driven system, so an hydrodynamic flow in the background that breaks Galilean invariance, then generically, there will be instability around the exceptional points or the exceptional lines that will destroy the phase. And to see it visually, what you can do here is you can go along that line and you see that there is an unstable flocking. So what you're going to see here is species A and species B, both the norm of the vector VA and VB and the angle. And whereas you would have expected in some region of this diagram from a mean field analysis that ignores spatial gradients than to simply align, instead what you find is that defects are continuously generated. There is a defect unbinding instability triggered by the presence of the exceptional points. And we analyzed this in detail and showed that it's a generic feature of the combination of the non-Hermitian L operator or non-normal operator plus a background flow. So there's an interesting take on, if you like, topological phase transition that is related to this non-reciprocity. And I believe that some version of this not I believe, it's true, some version of this in the context of mechanics was also studied by Ananio quite recently. Now, I was advertising that this phenomena also occur in the pattern formation. So let me show you how it works in pattern formation. Exactly the same model that I wrote, the one that described Vicsek, non-reciprocal Vicsek. This one here, if you interpret V to be the amplitude and position of periodic patterns, can describe, and with space translation invariance, can describe a non-reciprocal Swift-Homburg equation. What is the Swift-Homburg equation? It's a workhorse of dynamical system. It's a nonlinear PDE of this form. And there's a parameter R. And usually, depending on the value of this parameter, if R is, say, less than 1, there's no pattern. If R is greater than 1, there is a sinusoidal modulation or periodic modulation of this U field. Now, I want to do a little tweaking here and assuming that you have two fields that are now coupled, UA and UB. I don't have time to tell you, I mean, the Swift-Homburg model shows up in many situations, so I could cook up a physical story about it. Let me just present it in its dry mathematical aspects. Here we have two coupled non-reciprocal Swift-Homburg equation, and the coupling RA and B between the two fields B and A is non-symmetric, as usual in this talk. What happens then is that not only you have static periodic pattern separated by a given phase, you can also have moving one. And it's exactly the same mathematics as the VXEC model, except that now, in fact, there is again an exceptional point, a coalescence of a Goldstone mode due to translational invariance with a damped mode. But now, instead of having the broken symmetry being spontaneously chiral symmetry, you break spontaneously the symmetry between moving to the left and moving to the right. Okay, and generically, you can do this in many systems that display pattern formation. Usually, they're described by amplitude equations. This is quite common, and this amplitude equation can have non-reciprocal coupling between the amplitudes. Whenever that happens, you will generically have this type of complexity. And I'm going to show you some examples that have been studied, especially experimentally by people, but also a bit theoretically in the context of dynamical system already in the maybe 80s or something like that. I would like to stress that in this system with pattern formation, the reciprocal Swift-Homburg equation, besides the chiral phases that I showed, we can also identify those more exotic swap and chiral plus swap phases. So to show that those things are not just some exotic things that do not exist, you can find them even in this very simple system. And example of cases where not always recognized theoretically in the framework that we proposed, where these things show up are viscous finger experiments, eutectic growth, liquid crystal solidification, overflowing fountains. These are all systems that has non-reciprocity in the sense described here, that even have, certainly this one here, the same or very similar critical behavior that we described. In fact, our paper has an analysis of this system in the language that I just showed. But this one are naturally occurring systems, unlike the robots or the active system where you have to do some form of chemical engineering, etc., to get them going. So what I've tried to say here is that this exceptional point is transition show up in many contexts. I discussed in more detail synchronization, flocking, pattern formation, and this is largely, done in the context of Moduli non-reciprocal dynamics, if you like, which is the theory that we had written. More recent work has also explored other contexts, and I would like in particular to draw your attention to 3 papers that I know quite well, but I might have forgotten other stuff here, but just want to give you a sense that there's quite a community working on these things at the moment. This is a paper by the group of Cristina Marchetti, and deals with the onset of wave propagation in pattern-forming systems. And there's a paper in the group of Ramin Golestanian, and both of these papers consider, if you like, model B. So there are non-reciprocal system in the language I'm using here, but there's a conserved order parameter. They're a bit like odd elasticity. In odd elasticity, it's conserved order parameter because you conserve momentum in odd elasticity. So similarly, these are examples, in my mind at least, of model B critical dynamics. And there is also another recent work from the group of Sriram Ramaswamy that is here, and maybe he can add something himself later about this. So by no means isolated to the example that I consider. The final thing that I want to stress is that one thing that this talk doesn't do very well is to highlight the commonality of language between some of this context and similar discussion in open quantum system. I alluded a little bit about non-Hermitian quantum mechanics, but I want to just show you a simple trick. Like, imagine that you have an Hamiltonian system, but describing some Dreamer quantum system with gain and loss, okay? And now if there is gain and loss, this matrix will have, say, an I and a minus I along the diagonal. The I will give you the amplification, the minus I will give you the loss, okay? Now, this at first sight looks quite different from the non-reciprocity that I was talking about, right? This is just an Hamiltonian system with gain and loss. But now, look at the same thing in a different basis. Just rotate, okay? Literally apply this unitary transformation to this Hamiltonian IZ. What you get is another Hamiltonian that I've written here. Not an Hamiltonian, another operator, if you like. And this operator is just the antisymmetric matrix. Now, if this was hitting now on 2 modes, this will give you a non-reciprocal coupling between them. So there is a link between non-reciprocity as I defined, a system with gain and loss. And of course, this has been extensively explored in quantum context, only more recently, perhaps with an eye towards the many-body problem. I would like to advertise this paper by my two collaborators, Anai and Littlewood, in the context of quantum condensate. But I also would like to bring to the attention of the people in the audience who do quantum an old paper that I wrote with, well, old, I mean, it's 7 years, but with Philip Strack. Now, in this paper, it's not a very well-known paper, probably not a very important one. But what is kind of neat is that it's a quantum phase transition mediated by critical points that separate PT symmetry broken and unbroken phases. So it's the same, mathematically, it's the same type of transition that I showed. But both in the paper of Peter and Rio and in this paper, we go a little bit beyond what we did in today's presentation and studied the critical property. So the critical exponent. And in particular, one important feature of the exceptional point is that there is a generic amplification of fluctuations. This is quintessentially related to the non-normal character of those operators. I think Chiral in the context of sedimentation is something that in classical context has a lot of that flavor too. But one thing I want to leave it is that when we were doing, rather unawareingly, at least with Philip, 7 years ago, this calculation, we noticed this amplification of fluctuation near this critical point. And in fact, in order to capture them, more sophisticated functional renormalization group techniques had to be used. So in this model, if you like, the PT symmetry breaking transition is induced by strong nonlinearity. There is what people call a region field theory that describes a nonlinear ion chain, and it's quantum. And so let me just leave it that there is a lot of work now on this, on the quantum many-body level too. There's a lot on the single particle level, waves, etc., and non-emission things, but the many-body part is quite interesting, and I think it deserves additional studies also in terms of the critical properties. With that, let me say that our paper, as if this presentation was too confusing, as a visual, I don't know how to call it, a cookbook on how to approach this problem. So the first thing you do is you identify a system with macroscopic non-reciprocity and continuous symmetries. I stress macroscopic non-reciprocity because as evidenced in papers, especially by Ananio and Chiral, if I'm not mistaken, both of them were there, that you can have also microscopic non-reciprocity, even in flocking, in ordinary flocking, but it doesn't have to necessarily survive at the macroscopic level. But in cases in which it survives in the hydrodynamic equation, and you have a continuous symmetry, then you can follow the following pipeline. You write down the dynamical system, schematically represented like this. You find a stationary phase with a spontaneously broken symmetry, which could have a background flow, then things would be even more interested, or not. Then you linearize that dynamical system, and L would naturally pop up to be a non-Hermitian operator. And then you technically ask whether PT symmetry is explicitly broken or not, or spontaneously broken. If it's explicitly broken, there is a class of system, of which these particles that are spinning naturally by themselves are an example. If instead is spontaneously broken, is the analysis that I described today. And you can generically construct phase diagram that combine both of them. And so I refer you to our paper, which is quite voluminous, especially if you read the methods and supplementary information, which are probably the best parts, in fact, technically, and the many references in there. I hope that will give you an introduction to this field of non-reciprocal matter and the work that many of us are doing. Thank you very much for your attention, and I'm happy to take questions.
Thanks a lot, Vincenzo, for this really great talk. Thanks. So if there's a really urgent question, since we have kind of run out of time, if there's a very urgent question one can ask, or you can ask this question. Vincenzo, will you be able to be there for some more time in case someone has questions? Like we have this breakout room.
Absolutely, absolutely.
So I would say that if people have questions, maybe they can go to the breakout room and then ask.